In today's lesson, we're going to be learning all about intermolecular forces. So the first thing I want to do, I want to break that word down for us. Inter means between. So these are going to be the type of forces happening in between molecules. So this would be a water molecule, but when we're dealing with something like a whole bottle of water, we're dealing with a lot. So we never really look at one molecule by itself in the lab or in anything in real life. We're looking at a lot of water. So this deals with how these molecules interact and have a force on each other. So the other word that I want to explain here, so it's how these molecules are interacting with each other, is the word force. So all of these forces are going to be kind of a type of attraction here. So we could think of this word force as how attracted are different molecules, towards each other. Are they just a little bit attracted? Are they very attracted to each other? And that's what we're going to be looking at. So how attracted molecules are between each other. So that's what intermolecular forces means. So the first thing I'm going to ask us to do is to start off by forming a table that looks like this. So we're going to be talking about three main types of forces of attraction between molecules. And the first one we're going to be talking about is dispersion forces. So I'm going to write dispersion here. I'm also going to write down another term it goes by. It's a little bit less common, but you will most likely see it at some point in this class. London Dispersion Forces, also called LDF. So these are just dispersion forces. And the type of particles that we see these in are every particle. So this would be all molecules that includes polar and nonpolar. So I'll write that down just to be very specific. Polar and nonpolar. And then we also see it in atoms that don't want to form bonds. So all molecules, all atoms. And the reason that this force is in all molecules and all atoms is because it is caused by the random motion of electrons. Random motion of electrons. So let's take a look at this. Let's break this down. Electrons are in our atoms and they are constantly moving around, changing their spot, changing where they are. And if you have enough electrons moving around, it creates a temporary charge, just a little bit. So we're going to take a look at this. This is a neon atom. Neon has an atomic number of 10. So there are 10 electrons around it. So let's say one moment it looks like this, and the next moment it might look something like this, because those electrons are constantly moving. So you might think at this point there might be more electrons on this side, so maybe there's a partial negative on this side, partial positive over here. Over here you might have a very slight partial negative towards the top, and maybe on the left you have a slight partial positive. The important thing to get from this is that the electrons are constantly moving. So there's always a shifting partial charge, a shifting partial charge. So that's what I'm going to write here. Well, I guess that's what this is, a random motion of electrons, and it causes a shifting, because it doesn't always stay in one spot, shifting partial charge. So one last thing I want to talk about dispersion forces before moving on. We might have an atom like argon. Same thing. Argon is a noble gas, doesn't want to form bonds, just like neon. Except argon, instead of having just 10 electrons, has 18 electrons. The more electrons you have in your atom or in your molecule, the more random movement you're going to have, and the more possibility of it shifting and causing a partial charge. So that means the more electrons we have, the stronger our dispersion force is. So I'll write this in red. The more electrons in the particle, because it could be an atom or a molecule, so I'm just going to use the general term particle. The more electrons in the particle, the stronger the dispersion force. So that's why argon has 18 electrons. It has a stronger dispersion force. We could think of that as attraction, a stronger attraction than neon. All right, so that's all I got to say about dispersion forces, really. Let's make a line here. The next one we're going to be talking about, and these words I hope sound very familiar. This is called dipole-dipole, the next force. Dipole-dipole forces are only going to be in our polar molecules. So a molecule has to be polar in order to interact with each other with dipole-dipole forces. So this is polar molecules. And if we remember from last week, all polar molecules have dipole moments, which is the direction in that molecule that those electrons are pulled. So the cause of dipole-dipole forces, or we can think of it as dipole-dipole attraction, is the unequal sharing of the electrons. Unequal sharing of electrons in a molecule. So dipole moments are permanent. There's something built in to the molecule. So they have a stronger attraction usually than our dispersion forces. Because remember, our dispersion forces are caused by a shifting partial charge. Dipole-dipole forces are caused by a permanent dipole moment. So this bottom part of this molecule here is always going to have a partial positive charge. And by the oxygen up here is always going to have a partial negative charge. So when we have a lot of these molecules next to each other, they want to arrange themselves so that the opposite charges attract. So in this case, so that the partial negative charge is close to the partial positive charge. So that's how these would be happy sitting, just like that. They would not want to be like this, and they would not want to be like this. They'd want to have the partial negative and the partial positive closer to each other. All right, and we got one more type of force we're going to cover in this video. So let's make room. This one is called hydrogen bonding. And this is a tricky one because bonding is in the name, but it's not going to be a type of chemical bond. Hydrogen bonding is not a type of chemical bond. It's a type of intermolecular force, meaning it's just an attraction between these molecules still. So I don't want you thinking of it as a bond. I want you thinking of it as a type of attraction that certain molecules have. So hydrogen bonding, it's only going to be in very, very special cases here. So we need to have a nitrogen bonded to a hydrogen somewhere. or we need to have an oxygen bonded to a hydrogen somewhere in our molecule, or we need to have a fluorine bonded to our hydrogen somewhere in our molecule. So these are going to be, we could think of these as very, very strong dipole-dipole forces. So it's caused by, we're just going to write that down right here. A special, very strong dipole-dipole force. And I'll go into a little bit more detail in what exactly causes this to be such a strong force. Or we could think of it as such a strong attraction, because really, like I said in the intro, all of these are ways for molecules to attract each other. So forces, we could put attraction up here. All right, so we are going to look at an example to really understand the cause of this. So let me bump everything up here. We're going to take a look at HF, hydrogen bonded to a fluorine. And if you take a look at what this actually looks like, if you just look at the nucleus and the electrons, it's going to look like this. So you have to remember, hydrogen only has one electron. And when it bonds, it's sharing that only electron. So the electrons, even though they're moving, like if you take a snapshot, this is something that it might actually look like. And I want you to notice this. Look at this big old blank spot behind hydrogen. It's extremely vulnerable. It's completely open. The backside of hydrogen oftentimes doesn't have an electron on that side, which means it has a very strong partial positive charge. Remember, our nucleus is where our protons and our neutrons are, and our protons are positive. So when you have no electrons on this side, you're going to have a very strong partial positive charge. And then to balance it out, because the particle is neutral, or a molecule is neutral, we would have a very strong negative charge on that side. So these are just very, very strong partial charges here. Very, very strong dipole moment. And we would see something very similar to this in every bond between oxygen and hydrogen, and also nitrogen and hydrogen as well. So let me throw up some more examples here. This would be water. So you could see we got hydrogen bonded to an oxygen, and another one here, which would make this a very strong partial negative charge, and these strong partial positives. And it happens with NH3 as well, where it's pulling all the electrons towards that nitrogen, leaving these hydrogen exposed and strong partial positive charges. I want to give one more example, because those are all small molecules it happens with, but it also happens with larger molecules as well. So let's take a look at isopropanol. So this is a type of rubbing alcohol. And I want you to notice how many hydrogen are here in this molecule. So we got hydrogen bonded to all our carbons, but remember, these are non-polar bonds. So those electrons are being shared pretty evenly. So those are not hydrogen bonds. The only hydrogen bond here is the one we have formed between the O and the H. That is going to cause a hydrogen bond to want to form with another molecule. So this is a very strong partial negative. We got a very strong partial positive. So if something like water, which isopropanol is commonly dissolved in, came along, it would want to interact by putting the partial positives by the strong partial negative. So it might attract like that, or your strong partial negative might attract like that. So that would be a hydrogen bond right there. The attraction between this strong partial positive and that strong partial negative. All right, so I want to cover one last thing before ending this right here, and just to talk about in general the strength of attraction here. So we started off with our weakest strength, and as we go down, in general, it gets more and more strong. So I'm going to write increasing strength. And again, this is a generalization because you can imagine dispersion forces, if you have a huge number of electrons, if you have a very, very large molecule, dispersion forces can sometimes get pretty strong. So, but in general, if we're dealing with regular or kind of smaller size molecules, the strength will increase towards hydrogen bonding be the strongest, dipole being a little bit weaker, and dispersion forces being the weakest in general.